Well, good evening, everybody, and welcome to another lecture for Physics in Everyday Life. This is the 29th in our series of lectures, also known as the 6th, emanating from the corner of my basement. Nearly not as much fun as actually having class in person and doing some of the experiments we do, but, we're making the best of things and hope all is well with you out there. As always, if you have some concerns that would affect your performance in this class, please reach out and I'd be happy to work with you to try to figure out a path forward. So we're going to talk a little bit about the physics of alternating current and direct current, which I'm titling Edison versus Tesla because of the current wars that happened in our country about 140 years ago now. During this, we're also going to be talking about the basic operation of things like electrical generators and electrical motors. And if you've got a battery lying around the house and some wire and a magnet, you can actually craft an electric motor of your own, and there's a couple of videos linked in the slides further down that will show you how to do that. So last time, let's get on the right screen here. Last time we talked about magnets and the fact that magnets consist of two magnetic poles. One is called north and the other is called south, and they're named after the fact that a free spinning magnet, like a compass needle, points to the geographic north pole of the Earth. Like magnetic poles repel and opposite magnetic poles attract, we talked about the model for magnetism in that all materials contain magnetic domains, small regions that act like little mini magnets, and when all those domains are aligned with each other, the object acts like a more traditional magnet, a strong magnet. Magnetic fields are thought to exist around magnets, and magnetic fields also can tell us which direction say, for example, a compass needle or another magnet will align. So we don't actually have to think about necessarily the cause of the magnetism, like when we're navigating in Earth's magnetic field. We just know that the compass needle lines up with the field lines of the Earth. Finally, we talked a little bit about the use of magnets in credit card strips, even though that's on its way out due to security concerns. Many places still have you swipe the credit card, and when you do so, you're actually using the information that's stored on the back of that credit card in a series of magnetic north and south poles to input your information into the credit card reader. So we also talked a little bit about electromagnets last time, but that's kind of where we want to pick up the conversation here because electromagnets lie at the root of many of the phenomena that we're going to be exploring. So previously in the video in the last lecture, I showed that if you send an electric current through a coiled wire, that will produce a magnetic field, and you can make that magnetic field stronger if you wrap it around something like a nail that has a lot of magnetic domains and ferromagnetic properties rather than just having the coil in air, and you make yourself an electromagnet. And people have known about this for quite some time. In the 1800s, when a variety of people were messing around with how to make a telegraph, one of the schemes that ultimately got used to make a telegraph machine involved an electromagnet, like the nail model there. And so when a person on one end of that telegraph device, which is pictured there in the top right corner of the slide, would click a button and complete the electric circuit, on the other end, the electromagnet would be powered and could attract another piece of metal to make a click sound, and you could send a series of dots and dashes over that telegraph system. I don't know if you're at all a person that likes to read about history of science, but I found it pretty interesting to read the Wikipedia page on telegraphy and just all the kinds of schemes that people had once they knew that they could deliver electric current for how they could possibly deliver a message using this. Some people used 26 different wires so that you have one wire for each letter of the alphabet. There was a lot of different ideas floating around there for how to make a telegraph machine and transmit information. Another place you see electromagnets is a scrapyard. So very often on the end of a crane there, they'll put a large electromagnet, and when that electromagnet is powered on, it picks up all of the metals that are in that scrap heap that are themselves ferromagnetic. And then you can swing that somewhere else, turn the electromagnet off, and they will fall into the pile at that location. So these are a variety of simulations that demonstrate some of this phenomena of electricity and magnetism and the connection between those two. They're on the PhET website on the generator simulator, but the generator simulator is the previous generation. It runs on Java, and if you know how to work around the Java security blocks on your computer, you certainly are welcome to experiment with that generator simulator. If you're a Mac person, you can go into the security and the preferences and tell it that yes, it's okay to use this. I do not know how to get the workaround on a PC, but I'm going to exit out of the Google Slides for a minute and just show you a few of these phenomena in the simulator, because I think it's helpful to have a visual rather than just somebody talking about this. So here is the generator simulator, and it actually has 5 windows that give us demonstrations of things. You can also adjust various numerical quantities here, but I don't think that's particularly helpful for what we're doing here. So here's our bar magnet, and all of this is doing is showing us a visual on what the magnetic field looks like around that bar magnet. So in the previous slide, we showed pictures of filings, iron filings that were sprinkled on a magnet. They're acting like these tiny little compasses and indicating the direction of the magnetic field. And I think here I can move my large compass around wherever I'd like to in the field and see what direction it is, but it'll line up with those tiny magnets. Or I can drag my bar magnet around and change the magnetic field there. So this is simply a magnetic field, but what we really want to explore further is the connection between electricity and magnetism. And you can see a little bit of that in the next one involving a pickup coil. Now you can do this. I forgot to snag some actual coils from Begum & Hall and bring them here, so I'm relying on the simulated version. But if you take an electric coil and you move a magnet in the presence of that coil, you will actually generate an electric current in there. When you change the magnetic field that passes through this coil, it turns out this coil tries to fight against that change, and in doing so, it induces its own electric current. It's a phenomenon known as Lenz's law. And so if I move this magnet toward the coil, notice a current flows. Now if I stop moving it, importantly, nothing happens. If I pull the magnet away, current flows, but as soon as I get to the place where it stops moving, again, no current. So I actually have to be moving this. But in theory, here's my really crude generator. I'm moving this magnet back and forth, and I'm producing an electric current that is going back and forth in here as well. Sometimes it's pretty strong, sometimes it's not, so I'd probably want to get some sort of device that would move my magnet evenly. But that's the principle, at least. The simulator also has an electromagnet like we made. So here is a battery sending an electric current through a coil, but that is acting like a magnet. And you can see as I move it around, it adjusts the magnetic field. Or if I move this compass in the vicinity of this coil, it's producing its own magnetic field. There's no other magnet in the region here. A transformer is a device that actually uses current sent through one coil to induce a current in the other. So it's a combination of the pickup coil and the electromagnet. So notice here I got a battery and it's sending a current through this coil. That's producing a magnetic field, and that's the magnetic field that's visualized by all of these little compass arrows here. Nothing's happening over here in my pickup coil until, like I did with the bar magnet, I move my coil that's transmitting things here, and as I move it and change the magnetic field near the pickup coil, I can induce a current in that pickup coil and light the light bulb. And sorry it's a little jumpy here, but hopefully you can get the idea here. And you can also, instead of a light bulb, if you want to see a meter and see what's happening, you're inducing a voltage across that resistor that's shown there in that picture as you move your electromagnet back and forth. And you can alter as well the number of loops that are in here, though I guess 3 must be the maximum. And the more loops you have in that pickup coil, the more current you'll actually generate in this motion. We're going to revisit transformers a little bit later in the discussion, but I'll just show you the last piece of the simulator, which is a generator. And a generator involves a magnet producing a magnetic field. Now we don't have all those little tiny compasses, but we do have this compass that's telling us the direction of the magnetic field at any point. And now I need some way of moving this magnet so that I change the magnetic field around the magnet, and ultimately so I change the magnetic field in the middle of this pickup coil. So I don't know whose idea this was, but they made it, you drip water on this water wheel, and this spins the magnet. And in spinning the magnet, notice my magnetic field is constantly changing direction. And because the magnetic field is constantly changing direction within this pickup coil, I'm producing an electric current and lighting the simulated light bulb. Notice too that as the magnet spins in one consistent direction, sometimes the current is flowing in one direction, and then it'll reverse and flow in another direction, then reverse again to the original direction, and it'll keep following that particular pattern. And so here I am using mechanical energy to produce electrical energy. And this would be known as a generator. The reverse of this is a motor. We'll talk about that on the next slide. All right. So again, if you know the Java bypass, this is the generator simulator on PhET, but they haven't built an HTML5 version yet, unfortunately. Come on, Google, you can do it. There's only billions of people in the world using you right now. So we want to talk just a little bit more about motors and generators. I made mention of this when I was showing the simulator tabs there, but an electric current that moves through a wire creates a magnetic field. And if this magnetic field interacts with a permanent magnetic field, it can be used to produce motion and create a motor. So you can, if you push a current through a wire, and usually you'll see that wire wound in a coil, produces a magnetic field in that coil. If that interacts with a magnetic field from a permanent magnet, you can get that coil to turn and produce motion. And that's the basic idea behind a motor. So a motor is a device that converts electrical energy into mechanical energy. The reverse is if you instead take a permanent magnet and you move it in the region of a conducting wire, the changing magnetic field from that moving magnet is going to induce electric current in the wire, and that electric current then is used to power various devices, and this device would be known as a generator when you're taking mechanical motion and you're converting it into electrical energy. So there's a few videos that are over on the side. If you are following along the Google slides, they're linked in the announcement. If not, I took a little generator device that I have in the lab and used it as a generator to power a light bulb, but then also connected it to a battery to see what would happen. So that's the video in the top right of this particular slide. And then if you're curious and bored and have time on your hands and happen to have a magnet and some wire at home and want to make your own electric motor, I've put a couple of videos with links of how to do that. They come off of YouTube, and if you just go to YouTube and say how to make a motor, there's a dozen more on there, so you can take your pick of which one you like the best there. So direct current, as we've seen before when we talked, for example, about flashlights, is produced when you have a constant voltage or a constant electric potential difference across the battery, and it creates a current that always moves in one direction. So if you have, for example, a traditional D-cell battery, the positive side is known as the high voltage side of this, and the negative side is known as the low voltage side of this, and we get an electric current that flows from the high voltage side around to the low voltage side, and if that passes through the light bulb filament, you'll get the light bulb to light. Recall that again, even though current is actually, if you think of current as the flow of electrons, it's going from negative to positive. The convention is to talk about current in the direction from positive to negative, the direction where those gaps or those electron holes are moving. In truth, it doesn't matter too much for our discussion here, as long as you get the idea that direct current is a one-way direction of current flow only. By contrast, alternating current, which we saw a little bit in that last tab in the simulator, is current that switches direction periodically. And most of our electrical systems in the US, I believe, are set to be at about 60 hertz or 60 cycles per second. The current is switching direction. To do this, you need a varying voltage, and one of the ways you can get that varying voltage is to move a magnet in the presence of a pickup coil. and this produces an alternating current that switches direction periodically. So sometimes your voltage is going to be high, and then sometimes your voltage is going to go back to zero, and then sometimes the voltage will go negative maximum back to zero, and you get this wave form of voltage as a function of time. So if you look at the electrical outlet that we have there on the slide, if this is wired correctly, and at least if your house is like my house, that's no guarantee that it's wired correctly, the left, the taller side of an electrical outlet is always kept at a zero voltage state, and it is neutral. And in some sense, it's acting like a ground, though there's an additional ground prong in the circuit, and we'll talk a little bit about that towards the end of this discussion. So when you have an alternating current, that other side, which sometimes is called the hot side by electricians, is, let's say, for example, starting out at high positive voltage. Well, if that's at high positive voltage, then current is going to be flowing around the circuit in a clockwise direction, and that would correspond to these parts of the graph where my voltage is positive. But a little while later, the voltage would now actually go to being low or negative or beneath the value of the neutral zero voltage terminal. And so now the neutral or zero voltage is actually at a higher voltage than the low side is, and this causes the electric current in the circuit to switch directions of flow. And so you go clockwise, now back counterclockwise, then a little while later it switches back to being high on the hot side, and the current is flowing clockwise, and this pattern repeats over and over again. You don't notice your light bulb flickering on and off because that light bulb filament, again, is a filament that heats up, and it takes a little while to heat up, and it also takes a while to cool off. So if the current is switching really rapidly, 60 times a second, that filament is essentially always going to stay aglow while electric current is being provided to the light bulb. So we get to our first poll everywhere survey question of this particular lecture. At least in my head, alternating current is a lot more complicated to think about than direct current. And it turns out if you do the mathematics, that's more complicated too. So why in the world would we use AC circuits? You're not expected to know the answer to this question. I'm just curious what you think. So option A, physicists are evil and they try to complicate our lives. That's always true. B, light bulbs work with alternating current, but not with direct current. C, power companies make more money selling you AC than DC. D, you can make more power with an AC circuit than you do with a DC circuit. Or E, some other reason. So I hope you'll pause the discussion quickly and answer that, and then come back and restart. If you happen to do that, good for you. If not, I'm going to talk about this anyway. The answer, in my mind at least, is some other reason. Okay, you can have your opinion of physicists one way or the other. We don't think we're trying to complicate people's lives, but you may have another opinion. Light bulbs actually work with both. We started out actually by exploring incandescent light bulbs with direct current circuits like a flashlight, and that's where current is going in one direction. But you can also use a light bulb with an alternating current circuit. Now, different light bulbs generally have different voltage maxima, so I can't in general take the small light bulb out of my flashlight and plug that into the socket in my house, but I can use an incandescent bulb in either one. Power companies, I don't know if they would make more money. It turns out they would lose more energy if they delivered you your current via DC than AC. So in reality, because they want to lose as little electrical energy getting the power from the power plant to you, they end up going with alternating current, and we want to explore why that is. You can make as much power with AC or DC. It just depends on how much voltage you produce and how much current flows in that circuit. So the real reason is AC is superior because you end up losing less energy in the transmission of this. So in the late 1800s, there was a period of time in the U.S. known as the Current Wars. So electricity had been known about. People had begun to build electrical devices. The Industrial Revolution was happening. Electricity was being used in factories and the like, but most homes still did not have electricity. One of the first innovations that actually happened in places where people lived was they put some arc lamps in the cities, and it turned out that the arc lamps in the cities worked better on AC voltage than DC voltage. But in order to do that, I read, I think, that most of these AC lines in the cities were 3,000, 4,000 volts and not super well protected and not probably widely understood. And so there were some horrific accidents where members of the public died. Well, still, people realized the promise of putting electricity into people's homes. But obviously, this was an engineering challenge. How do we do this? How do we deliver electricity to folks' homes? So Thomas Edison had a big company and was well known at the time. And he started pushing for a system of putting direct current into people's homes. And one of the reasons is the direct current was delivered into folks' homes at much lower voltages than the voltages in the AC systems that were being used to power the street lights outside their houses. So this low voltage DC was not as dangerous in the home. So Edison was championing DC methods of delivery. And he actually worked with an engineer named Harold Brown. Harold Brown was actually the public face of much of the wars that came out in terms of which kind of current should we be delivering. The other side of the war was chiefly a guy named George Westinghouse, who was, I think, a relatively wealthy guy and owned companies. And I think, you may have heard the Westinghouse name still applied to like appliances. Well, Westinghouse, from what I've understood, wanted to actually start a rival power company to Edison's. One of the issues was if you started a rival power company to Edison and you were going to deliver DC power to folks' house, you had to obviously make some sort of modifications to the system that Edison was using so that you weren't considered to be stealing his intellectual property. Well, Westinghouse hired this engineer named William Stanley to figure out how the power should be delivered for this new company. And Stanley had actually known about European work by Tesla and others on making AC systems and understood some of the reasons why AC would inherently be advantageous for powering the United States. So he actually pushed Westinghouse over to the AC side, and so the Westinghouse company began to put in AC systems in certain places and win contracts in certain places, while Edison had contracts in other places. So there was decades in the U.S. where certain cities were powered on DC and other cities were powered on AC. I think it was the Chicago World's Fair, I want to say, in the late 1800s that famously brought in the Westinghouse system of AC and electrified everything and wowed the world. But Edison had a pretty good size of the market share for quite a while. And this war got heated, right? If you're fighting over turf and who's going to make the most money electrifying the U.S. houses, you can imagine that people had some stakes there. So I've heard stories, and I don't know if this is true. Harold Brown, who worked for Edison, this engineer, held public displays where he executed retired circus animals via AC circuits to demonstrate the supposed danger of high voltage AC circuitry and trying to convince people you don't want this in your house. You need this safe direct current. Well, they eventually lost because AC is actually fundamentally superior for delivering electricity. Westinghouse ended up buying several, I think, of Tesla's patents, and Tesla was a brilliant scientist who actually came up with many of the ideas for how you could create alternating current, how you could deliver it, how you could change voltages of it. And another story I've heard that I don't know the truth of is that Tesla understood the mathematical nature of all of this stuff, but Edison was never a very good mathematician, and so at least some people contend he never even really understood AC method of power delivery very well. Ultimately, the AC won out because you and I have in our homes AC outlets that deliver a changing electric current. I think about 60 times per second the direction of that current changes. So why is AC superior? Why did AC eventually win out? Well, the power company has a dilemma when they want to get electricity to your house. Obviously, they have to use wires to do so, and the longer the wire, if you make wire longer, it has more resistance to it. Resistance is actually proportional to the length. So if you make the length twice as long, you make the resistance twice as much. And the greater the resistance, the more heat you produce as the electricity flows through that wire, the more energy you lose between the power station and the person's house. And so whether or not you would get that passed on to you as a bill or the power company would eat that loss, that's not something anybody wants to have happen. Recall from a previous discussion that we've said, at least in the context of electricity, that electrical power is the product of voltage and current. But if we take Ohm's law, which says that voltage equals current times resistance, we can write a new form of this power equation that's helpful in thinking about what happens with electrical energy delivery. So if I replace the voltage in the power equation with current times resistance, my new power equation says power is equal to the square of the current that's flowing through the wire times the resistance. And so either of those things, increasing the resistance in the wire is bad for power delivery because that's going to also increase the heat, but also increasing the current flow through the wire is dangerous. Not dangerous, but expensive, because you increase the current, you increase the power loss as well. You want to get a certain amount of power to the customer, right? A certain amount of energy per time. And so the way to do that, if you want to do that at a relatively low current, is to do it at a high voltage. And so that's in fact what's done in AC systems. You have a power plant, and they might produce voltage at, say, 12,000 volts. Well, they don't actually want to send that over lines at 12,000 volts. They'll still lose too much energy. So they send this through something known as a step-up transformer and change it to, say, 20 times that, 240,000 volts. Electrical energy is then transmitted on high voltage lines at this 240,000 volts or 500,000 volts or 1,000,000 volts. And then nearer to your house, it goes through a series of step-down transformers, substations, and additional step-down transformers in your neighborhood before being delivered into your home as 240 volts. And you'll feel it if you touch 240 volts, but it's not nearly as easy to kill yourself with 240 volts as it is with several thousand volts. Why AC? Well, AC actually makes it possible to use these transformers. DC cannot use these transformers, and while there are some ways to change voltages in DC circuits, it frankly isn't very practical to do. And so one of Edison's dilemmas was that DC could not be transmitted over long distances. And so if Edison had won out, we would all have neighborhood power plants that were relatively close to our house because the power company would not want to send the electricity over any great distance because they would lose a good portion of that energy before it even got to your house. DC did stick around, though. There was the last place in the U.S. that was known to be wired for direct current switched over in, I believe it was 2007. It was a hotel in New York City. So even into your lifetime, there were places that were wired for DC in the U.S. So let's take a couple of more poll everywhere survey questions and think about this relationship about power. So if you imagine we have some power lines that are 10 kilometers long and they lose, let's say, 5% of the energy that's transmitted through them. If you now make these power lines 20 kilometers long, so you double the length, but you're delivering the same amount of electricity, same amount of current flowing through, how much energy is going to be lost here or converted to heat? It's going to be 5%, 10%, 20%, 50%. Again, you're encouraged to pause the presentation and answer the question before moving on. The second question, power lines that are 10 kilometers long lose about 5% of their energy transmitted through them. But now if you need those power lines to send twice as much current, how much energy is going to be lost or converted to heat? 5%, 10%, 20%, or 50%? The answer to both of these questions lies in that relationship that's at the bottom of the slide. If you take a wire that's losing a certain amount of energy and you double its length, you're going to double its resistance. And in doubling its resistance, you will double the amount of power that's lost. And so doubling the length would now lose about 10% of the energy. If you take the same wire, don't change the length, but now ask it to deliver twice as much current, The power lost is actually proportional to the square of the current. And so if you're losing 5%, 5%, and then you square the current, if you double it, doubling the current squared means you now lose 4 times as much energy. So it's about 20% of the energy that would be lost in that situation. So again, ultimately, power companies want to get that voltage as high as they practically can for transmitting it over long distances before stepping it down to safer voltages near your house. To do that, they have to use something called a transformer. It is not the transformer over on the right where the car changes into the robot and vice versa. It is instead the much more mundane looking power substations that you may have seen somewhere around your neighborhood. So you can deliver the same amount of energy per time, same amount of electrical power, with low current and high voltage, or high current and low voltage, and we've talked a little bit about why it's advantageous for that to be high voltage, low current. And the device using to do this is called a transformer. So a transformer doesn't look exactly like this, but is fundamentally some sort of core, and it's often iron or something like this that can be magnetized. And so if you have this iron core, what happens is you wind wire around one side of the iron core, and you wind wire around the other side of the iron core. Then you hook the side known as the primary side to your source of energy. So electric current flows into that primary side and goes around the coil. In going around the coil, it produces a magnetic field. Well, that magnetic field is everywhere within the coil, within the core rather. And so the other side of the core also gets a magnetic field in it. And that magnetic field within the coil on the secondary side actually induces a current and causes current to flow on the secondary side. But you can change voltages related to the number of coils that you have on each side. It turns out that if you want to increase the voltage on the secondary side, you have to put more turns of wire over there. More turns of wire means that when a magnetic field is set up on that secondary side, you will get a bigger energy difference or a bigger voltage out of it. If you want to step down the voltage, you put fewer turns on the secondary side than are on the primary side. And so in the diagram, it's showing a step-down transformer where there are fewer turns on the secondary side of this, more turns on the primary side of this. But if you just made more coils of wire on the right than left, that would be known as a step-up transformer. So theoretically, and these relationships are hinging on the idea that energy is not lost in this, the secondary voltage is equal to the primary voltage times the ratio of the number of turns. So if I have 2 times as many turns on the secondary side as the primary side, I'm going to get twice as much voltage on the secondary side as I will on the primary side. Of course, you can't get energy for free. So if voltage goes up, current goes down, and the current on the secondary side is equal to the current on the primary side times the number of turns on the primary side to the number of turns on the secondary side. So if, for example, what it looks like in this diagram, I have, twice as many turns on the primary side as I do on the secondary side, I'm going to really end up getting twice as much current on the secondary side, but only half as much voltage. Again, changing the number of windings is going to change these ratios. So the last thing we want to touch on in terms of a device in this discussion is converting AC to DC. Excuse me. Lots of things in our lives run on batteries, your phone, your laptop computer, etc. And so if they actually run on batteries, they are generally engineered to run on direct current. But we don't want to run out and buy new batteries every time those batteries wear out. We would like things to have rechargeable batteries, and rechargeable batteries require plugging into an electrical outlet and also having the ability to be powered out of an electrical outlet through an AC circuit rather than a DC. So what you ultimately need then is a device that's going to take some electrical energy out of an AC power outlet and convert it into direct current. And so power adapters, all those little brick-like things you plug in and heat up as you're charging your various devices, use a circuit that has 3 electrical components in order to accomplish this task. They have something called diodes, which we'll talk about here very briefly in a moment. They have transformers, which we've just talked about for the purpose of changing one voltage level to another. And they have devices called capacitors, which again we will talk about here momentarily. Before we do so, though, an example of problem solving. This is an AC adapter, and you can see in the picture here the AC adapter says the input voltage is 120 volts AC at 60 hertz and 250 milliamps. A milliamp is a thousandth of an amp, so that's 0.25 amps. The output is DC. It's 9 volts DC, so this could be used to power a device that generally ran on a 9-volt battery. And it produces 1,000 milliamps, or 1 amp of current on the output side. So this power adapter uses a transformer, several diodes, and a capacitor to convert high AC voltage to low DC voltage. So what is the ratio of turns in the transformer that's inside there based on the voltage information we have? And then what percent of electrical energy input becomes electrical energy output? I encourage you to try to solve that problem on your own using the relationships on the last few slides. If you want to see my walkthrough of the solution, it's in the YouTube link that's embedded if you're following here in the Google slides, or linked in the announcement of this lecture that came out. So, what percentage of the electrical energy input becomes electrical energy output? Is it less than 25%? Between 25 and 50%? Between 50 and 75%? 75 and 100%, or is it 100% efficient here? I'm not going to go over the answer here, but you can go back a slide and look at the YouTube video or work out the problem if you've not already done so to figure out what the correct answer is. All right, so we want to talk a little bit about diodes and capacitors, and a fun way I think to introduce the concept of the circuit that they build together is this little puzzle on one-way streets. Completely up to you, but this is linked as a document in the announcements, and if you want to print it out and try it, if you like puzzles, I would encourage you to do so. The way this is supposed to work is that all of these intersections are streets, but at each intersection you have to follow an arrow, and you have to make smooth turns with a curve. You can't back your hypothetical car around a corner. You can't do any U-turns, and you can only leave an intersection at the head of an arrow. So what does that mean? Well, if I started at start here and I come into this first intersection, I could go straight because there's a straight arrow that goes through and an arrowhead that points me right. I could also curve to my left and end up going up on the map right here because there is that curve and the arrowhead up here. But I could not go down because that would involve a sharp turn here in the middle. I'm not given that curve to indicate that that's a legal turn. So the first intersection, I could either go left or straight. Well, if I go left, then I have to go around this corner, and then I have to go around this corner because there's no option of going straight. Whereas if I go straight here, I could then go straight at the next intersection, or I could curve to the right, but I could not curve up and go upward because there's no arrowhead there. So if you like puzzles, feel free to print it out and see if you can actually navigate your way to the finish through this series of one-way streets. However, the trick is they're not always one way in the same direction. All right, what in the world does that have to do with power adapters? Well, again, we've got to talk briefly about two devices. The first is known as a diode. And a diode is a device that's kind of reminiscent of the photoconductors we talked about during the photocopying lecture. So it acts like an electrical insulator when current is flowing in one direction, meaning it doesn't actually let the current go through very much at all. And it acts like an electrical conductor when current's going in the opposite direction, meaning there's an easy flow of charges. So I pulled the diagram of the hopping charge out of a previous edition of this book, but all we really need to know at this point is that these diodes act like one-way streets for current flow in a circuit. The second piece of this is a capacitor, and a capacitor is a device that has two electrical conductors and they're separated by a gap. So I can even make a crude capacitor. I take a piece of aluminum foil and have two pieces of aluminum foil held together but not actually touching is a capacitor, because if I connected this to a battery, charges would be stored on these two aluminum plates, and they'd be held there until I did something with that charge. Whereas if I have these two pieces of aluminum foil touching and then I touch a battery, I'm going to get a continuous current to flow. No charge will build up on these sheets of aluminum foil, and I'll actually short the battery out and kill it prematurely. So capacitors in a circuit look something like this. You can also see flatter, round-shaped capacitors. There are various shapes that get wired into various circuits. But if you want to have a little bit more understanding of how a capacitor works in conjunction with a battery, and then in conjunction with being able to power something on its own like a light bulb, I would encourage you to click on the link there at the bottom of the slide. That takes you to the PhET capacitor simulator, and you can play around with a virtual capacitor and see how it functions. All right, finally we've arrived at our physics of our power adapter here. So inside a power adapter, there's three devices, and this is actually a photo of the elements taken out of a power adapter. You have this little thing, which you might be able to see some coils of wire there. This is your transformer, changing one voltage into another. This is a network of 4 diodes, those little cylindrical shaped elements that we saw on the last slide. And finally, a capacitor over here, and then the 2 leads that go to whatever device I'm going to be powering with my power adapter. How does this all work? Well, below is a circuit diagram, sort of a street map of what's happening here. And we're going to think through this one piece at a time. So here I have alternating current over on the left, which means it's sending current in first in the clockwise direction and then the counterclockwise direction. And its current goes through this coil that's wound around the primary side of my transformer. On the other side of my transformer, I have coils as well, but there are fewer of them, so I'm going to be stepping down the voltage. And the transformer is the device that takes the 120 volts and steps it down to 9 volts. But it's still AC over here. It's still changing direction because a transformer doesn't do anything to change AC into DC. In fact, you can't use a transformer with DC because if you send a constant current through a coil, it produces a constant magnetic field, and a constant magnetic field won't produce a current on the other side of the transformer. You have to have AC for transformers. So let's just think about a situation where in one moment of time, electrical current is flowing to the right here on the top of the secondary side of the transformer. Well, then it runs into this diode network, and it's got diode 1 or diode 3. But it can only flow through diode 1 because of the direction of these arrows here. And so it's going to flow up through diode 1. Diode 3 is essentially acting like an insulator and does not allow any of the current to go down there. It reaches this point up here, and then again it can't go through diode 2. That would be the wrong direction, so it continues over to this portion of the circuit where it has both the capacitor and the hypothetical radio that we're powering with this adapter. Well, current is going to flow down to the capacitor and start charging up that capacitor, but at the same time current is going to flow to the radio and provide electric power to the radio. The purpose of the capacitor is actually to act as a temporary storage bank for charge. When the current is really high at the top of that AC wave, there's a lot of current going here, and I don't want all of it to go to my radio, so I store it with my capacitor. Then, when the current is actually low, the capacitor will release excess charge, and that charge will flow through the radio, and it keeps the current going through the radio at a relatively steady rate. Current flows off the other side of the capacitor and through the radio, and it combines down here on the bottom side of this circuit. And then it reaches a junction, passes through D4, and then back, and that little jump is a bridge showing that those wires aren't actually electrically connected, back all the way to the other side of the secondary coil. So this is the direction of the current flow at one instant in time when the AC current is flowing in one direction. Well, a little while later, the AC is flowing the opposite direction over on the left-hand side of this circuit. What will that do over at my radio? Well, let's start the argument here again. So now I got current that's going to the right on the lower side of my secondary coil. So let's trace that path. Going to go down here, cross the bridge, and get up to the diode network. And again, it could flow through diode 2, or diode 4, but diode 4 is flipped around, so it is a insulator path for the current. In that context, nothing can go through D4 from this direction, so the current's all going to flow through D2. And notice it gets to that point where it got when current was flowing in the other direction. So this 4-diode network is actually what reverses the direction of the current half of the time, so that all the current coming out of it is always in the same direction. Current's going to go across the top of this network, once again charge up the capacitor, once again flow through the radio. That capacitor again will power the radio when we get to a low part of the current wave, but current comes through the radio and off the other side of the capacitor, again back through this diode network, back through diode D3, and back to the top of the secondary coil. So again, it's flowing in the opposite direction near the transformer, but in the exact same direction over there on the side of the radio. And so we've successfully used 3 electronic devices to convert AC at high voltage to DC at low voltage. So it wouldn't probably be a great service to not talk at all about the deleterious effects that electricity can have, and to just give small warnings about electrical safety. So a couple things is that the amount of electrical current that flows through you as a human can depend on what kind of feeling you get. So in general, when we work in labs and such, we use things like batteries that are 1.5 volts, and if I touch the 2 ends of this battery, I won't feel anything. There may be a very small current flowing through me, but you have to get it up to even 1 milliamp to get a mild tingling, and I'm not getting anywhere near that when I touch those 2 ends of that battery. But muscle spasms occur for most people somewhere around 1/100th to 2/100ths of an amp, and so if you increase the current tenfold from mild tingling, you'll get muscle spasms. You start to cause problems in your heart if you go up another order of magnitude, somewhere in the 0.2 of an amp range. And if you send a sustained current, and just for a few seconds, of 1 amp or more through a person's heart, it will actually stop your heart from beating because it messes with the electrical signals there. So obviously, electrical current is not something to joke around with. Now, you might think, wait a minute, in my house there are circuits that are 10 amps and 15 amps and 20 amps. Am I going to die? Well, the answer is no. The devices you are connecting to those circuits generally have a good conducting path through them, and so they're made to carry a high amount of current. Your body is not generally a good conducting path, though there are some exceptions to that. And so your body has a lot more resistance than your toaster or your light or whatever you're trying to plug in. So you in general get much less current through you. It's still not advisable to go stick your fingers in light sockets, but it's generally not going to kill you if you do so for short periods of time. Now, why that third plug on grounded outlets? Well, here's a little diagram I stole out of another physics textbook. That shows, okay, I got my electrical dryer, and most of the energy in an electrical dryer is being used to power that heater to produce the heat to dry my clothes. And so what happens if I just use a true prong plug in that? Well, I have an alternating current circuit, and current's going in one direction through one wire, through the heating core, or the heating filament, and back the other direction through the other prong of the plug, back to the circuit, no problems. And that current will continue to keep switching directions unless something goes wrong. And the something goes wrong could be, for example, that this wire frays and now comes in contact with the casing of the dryer. Well, if that happens, the electrical current flowing through there wants to get to a lower energy state. It wants to flow to ground, and the route to ground is then through whomever is touching the dryer, and that current uses you to complete a circuit to get back to ground, the low energy state. If instead I actually have the casing of the dryer connected to the ground wire, that third wire in a circuit, then even if that wire breaks in that heater, the current will not flow through you because you still have more resistance than the metal casing of the dryer. It will instead flow through the metal casing of the dryer, through that ground wire, and be safely discharged to ground in that electrical system, not through you. So Moral of the story is things are grounded for a purpose, and particularly devices that use large amounts of electrical current, and it's never a great idea to use those little plug adapters and remove the grounding feature of your electrical plug. Electrical safety, just a few notes on here in one gross picture. The common idea that a lot of people have is that voltage kills. High voltage is inherently dangerous. It can be. People died in early cities as they had those high voltage AC arc lamps at a few thousand volts. And certainly I would not encourage anybody to ignore the signs that say danger, high voltage. But in reality, it's more than voltage. If you've ever seen a Van de Graaff generator, there's a picture of a woman with her hands on it there, those metal spheres, and you put your hands on there and you charge it up and your hair stands up and everybody laughs. Those routinely actually charge to a voltage of 50,000, 100,000, even 200,000 volts. The secret is they can't store that much charge on them because they can only store charge over the size of that metal sphere. Whereas if you have a 250,000 volt power line, it is connected to a vast network that stores a lot more charge than you can store on the Van de Graaff generator. So high voltage in and of itself is not necessarily dangerous. It's actually the amount of current, the amount of charge that flows through you that ends up being harmful and or fatal. Current actually, when it flows through you, causes your muscles to contract, which increases the risk of being electrocuted because, for example, if you, I don't know why you would do this, but if you're saying, is this wire live, and you touch it and it is, it's going to make your hand grasp the wire and not be able to let go. And so that picture is somebody who didn't make it after having been electrocuted on a wire. And they tell you, and again, I have a hard time thinking about when you would need to know this in your everyday life, but life's crazy now, so who knows, maybe this is useful advice. They tell you if you ever had to test something, use the back of your hand, because if this was live and it caused your muscle to contract and your hand to grip, you could still pull it away because you wouldn't be stuck on the wire. Body resistance actually varies widely and can vary depending on, how much you're exercising and all that kind of stuff. And so you can't really say, my body has 400 ohms of resistance and calculate how much current would go through it. And the resistance varies widely, and that is going to vary how much current can flow. But in general, bodies have relatively high resistance. And unless you encounter something like a high voltage line connected to a big power grid or a lightning strike, you're not going to get significant amounts of current flowing through you and not going to have those harmful or fatal effects. Finally, there's a reason for the grounding and polarizing features of plugs, and so it's worthwhile to make sure that in your home things are wired correctly, and also worthwhile to not bypass those electrical safety features with plugs that, for example, reduce 3-prong down to 2, because you are making it more dangerous if something goes wrong in that electrical device and you need to have access to that ground to dissipate the excess charge. So that's what we wanted to cover in this particular discussion. We talked a little bit about electrical energy and how it can be delivered via DC circuits, direct current circuits, or AC circuits, alternating current circuits. AC is fundamentally advantageous for power distribution because you lose less of the energy in getting the electricity from point A to point B. You can step up the power to high voltage, low current, transmit it across those high voltage lines, and then step it down to lower voltage and higher current when you get it near the residential places where you want to use it. Finally, we talked a little bit about power adapters, and power adapters being devices that transform AC back into DC. They use a network that has a transformer to change the voltage, a network of diodes to change the direction of current flow, all to being a single direction, and then use capacitors to store charge when the current is high and release charge when the current is low to even out the current waves and provide a constant amount of direct current to the device that you are trying to power. If you've not done so, I would encourage you to look at section 11.2 in the book. That's where Bloomfield talks about similar topics to what I touched on in this conversation. The Chapter 11 quiz is available as of 2 p.m. on Friday, April 3rd, and will be available until 2 p.m. on Monday, April 6th. So you should log in and take that. And if you want to look ahead to next time, we're going to be talking about the content of Chapter 12, Section 1.